So, welcome to this fourth lecture, mathematical model of T and Tm mode, the two remaining, and also we will discuss the impedance concept in this one. So, already you have seen the model for Tm mode. Now, we already have seen the T and Tm conditions. Now, we will just put that, and in T and Tm it is much easier, because if you remember that equation 15 was an expression of all four transverse fields in terms of longitudinal fields. Tm wave, there was a problem that since everyone was becoming 0 by 0 and Kc was also becoming 0, but here there is no such problem. So, transverse electric field, let us see that we know the condition Ez is 0 and Hz is not 0. So, since one of the two longitudinal field exists, we can use equation 15 directly, just unlike Tm case, which created some problem by becoming 0 by 0. So, you can find out what is Hx, what is Hy, Hx in terms of Hz, Hy in terms of Hz, Ex in terms of Hz, Ui in terms of Hz. So, in T case, if you can find Hz, you can find all of these. Good. So, Hz, from where I find Hz? From Helmholtz equation, because Helmholtz equation of a or wave equation, that is same. So, all four transverse components depend on Z. So, Hz should be determined from Helmholtz equation for Hz. Helmholtz equation for Hz is this. Now, also we know that Hz can be written as this transverse component, this is a magnetic field transverse component, into we know the Z variation, wave is propagating in Z direction. So, e to the power minus j beta z. So, putting that, this becomes this, you see Kc square this. So, this is a second order differential equation, and by applying proper boundary condition that will be required, you can always solve for this Hz. Once you know Hz, you know all the four terms. And the other things, phase constant and cut-off wave number, those two, the beta and the Kc. So, how will you find? So, unlike Tm mode, T mode has a non-zero cut-off wave number. So, all frequencies cannot propagate as a TE mode. So, it has some finite value, and phase constant is a function of the source frequency and the geometry of the line, because this Kc, that depends on the geometry of the line. K depends on the, K is what? K is a constant, omega square mu epsilon. So, it depends on the material and frequency. So, T waves can be supported inside single closed conductors, waveguides, no problem, as well as between two or multi conductors. So, in a coaxial line, in a multi conductor line, T modes can always exist, but above a certain frequency. That depends on the thing that you can always find out from the, for any given case, that from which frequency you will start having T modes, but it is supported. So, you see this was all about T mode. Just to, if I go back, you put that condition in that, you find all the fields, then Hz is written as a second order differential equation. You have the structure that you are having, put the appropriate boundary condition on Hz, and you get, like if you have in a waveguide. So, what is Hz? I know what is the boundary condition. Here I know it is a metallic thing. So, Hz will be tangential to it. So, on this face it will be 0. Similarly, on the bottom face also it will be 0. Now, here it is a normal component on this transverse plane. Now, there you will have to see that here, suppose in this wall, this is also a metallic wall, and Hz is again a transverse field here. So, that will be also 0. So, enforce this, that will give you the Hz values. So, depending on the problem you will have to do that, and then you can always find this beta t and Kc etc. So, beta t you can find as we have already shown. Now, similarly is transverse magnetic modes, you have the condition here is Hz is 0, Ez is not 0. So, again put it into equation 15, then you get 43, equation 43, that all Hx, Hy, Ax, Ay in terms of Ez. So, solve Helmholtz equation for Ez, and it is again once you solve Ez, you can find out what is the beta mode. Again this is it has a cutoff number and phase constant. So, TM waves also can be supported inside single closed conductors waveguide as well as between two multi-conductors, two or more multi-conductors. So, in all structures you can have this, but above a certain frequency given by the cutoff frequency. Now, let us come to the concept of wave impedance, not characteristic impedance. What is wave impedance? Wave impedance is related, it is a characteristic of the wave. It describes the radiation property of the wave. It is the ratio between the two corresponding transverse electric and magnetic field components that carry the power in the propagation direction. Please understand this a bit carefully. You see, suppose the wave is propagating in z direction, and let us say that I have all these Ex, Ey, Hx, Hy component. Now, what we say is that you take, you see the here the important part is this corresponding is important, ratio between two transverse electric and magnetic field components. Now, if you say that okay, I will take Ex by Hx, is that wave impedance? No, this is not wave impedance. Why? Because it is violating this corresponding thing. By corresponding, what we are saying? Corresponding electric, transverse electric and magnetic field components that carry the power in the propagation direction. Now, Ex, Hx, these two components are not corresponding components, they are not carrying power. Why? Because Ex cross Hx will be what? 0. So, it is not carrying any power. Ex means Ax direction, it is also Ax direction. Ax cross Ax is 0. But you see Ex cross Hy, this is creating power in z direction. So, they are corresponding, that is why wave impedance will be Ex by Hy. That is, now what are the other ones? Ey by Hx, am I correct? Again wrong. They are carrying power, but I need to carry the power in the z direction. Now, what will happen to Ey, Ay cross Hx, Ax? This will carry power in which direction? Minus z direction. But definition says that carry the power in the propagation direction. Propagation direction is plus z. So, in this case what we do? We put a minus sign here. That wave impedance. So, wave impedance is written like ZW. ZW is Ex, Hy or minus Ey by Hx. There are no other possibility. So, this definition corresponding that it carries power in this. This is the reason for negative sign in equation 36. Where is equation? You will see in the notes that equation 36 we have defined, where and reason is this, that wave impedance carries power, means it shows that ratio of the electric field to magnetic field. Wave impedance can be defined for T, TEM or TFs in a straightforward manner. You find out the fields, we have seen how to find the fields. In any particular case, you find out the fields, you find Ex component, you find Hy component, take their ratio, you also take Ui component and Hx component, then put a minus, take their ratio, that gives wave impedance. So, in a TEM case already we have seen, for a TEM case you have Ex and Hy, you take that ratio, that is their wave impedance. Wave impedance depends only on the frequency of the AC source and material properties of the medium. Wave impedance depends obviously on the frequency. So, if you change the frequency to 1 megahertz to 100 gigahertz, wave impedance will definitely change, because you know impedance is a frequency dependent term. But it depends on the material properties, omega, mu, sigma, etc., but it does not depend on the structure where it is propagating. It describes the radiation property of the wave. What it says physically, what is wave impedance? You see, for plane waves, the wave impedance is always 377 ohm. Now, what is physical meaning of wave impedance? It says that what is the strength of the, when a wave is propagating, then what is the strength of, relative strength of electric field and magnetic field. And we say that if wave impedance, it is higher than 377 ohm, then it is a high impedance electric field. High impedance electric field means electric field is much stronger than magnetic field. So, a high impedance field, if I want to measure, then generally we use an E field probe. Whereas, when wave impedance is less than 377 ohm, then we say it is a low impedance field, and generally we use a magnetic field sensor to measure that field. You know that if I want to measure a field in measurements, I need not measure both the electric and magnetic field, because I know when they are propagating in free space, they are having the impedance, wave impedance. So, but wave impedance tells us that which one is predominant, E field or H field, whose strength is more. So, we try to measure that, and wave impedance is a very important property of the, it does not get affected by who is carrying that, etc., only the material and frequency of the source that governs the thing. It describes the radiation property of the wave. Okay. So, in the applications, as I said, that if I want to measure, etc., sensing applications, wave impedance is the important thing. Now, characteristic impedance, I have already said earlier that characteristic impedance, what is the concept from two-port network, that is basically an impedance, so that both sides you see impedance match. Now, for non-symmetric network it is image impedance, for symmetric network it is characteristic impedance. So, if you terminate by characteristic impedance, you see that the input impedance is same. So, that is why your from the source to the line, the power transfer is same. Similarly, if you put the source impedance to be equal to characteristic impedance of the line, then at the load side there will be match. So, the maximum power transfer will take place. it is not the property of the wave, it is not the property of the wave, it is the property of the transmission line supporting the wave. So, for a network, characteristic impedance is important. For the wave, from an antenna, no one talks of characteristic impedance. Antenna has input impedance, that is a separate concept, but it is not characteristic impedance. The wave that antenna radiates, we calculate is wave impedance. But for line, we say of characteristic impedance. For TEM wave, voltage and currents are, as we have seen, for TEM wave the fields are quasi-static. So, the voltage is a line integral, the current is a contour integral of the EM fields. Now, we know that line integral of anything depends on the line. So, it depends on which path I am taking. Contour integral also which contour I am taking. So, characteristic impedance, which is nothing but ratio of voltage and current, ratio of line integral to contour integral. So, it is a function of the geometry of the line. That is why different structures have different characteristic impedance. Obviously, it depends on the frequency of the source, material properties of the medium filling the transmission line, but apart from that, it also depends on the structure. So, what is the how much is the radius, what is the cross section, in all these characteristic impedance depends. Now, problem is characteristic impedance cannot be defined for TE and TM mode. Only for TEM mode it can be defined, because it is a quasi-static field, we can define a V and I. We have already seen that non-TEM modes, no voltage current exists, as quasi-static approximation is not valid there, the Laplace equation is not valid. However, microwave engineers, if you do some higher studies in microwave engineering, you will see that we actually we always prefer a voltage current description. So, we microwave engineers, we try to define, even for TEM modes also we define some amount of voltage and current, but that is beside the thing. But since I cannot say that we cannot do that. So, however, under some generalized constants at certain designated points only, we call it ports, where only we define that some voltage current, equivalent voltage current with these T and TM waves, but otherwise these non-TM modes. And so, the characteristic impedance is we do not define for T and TM modes. We define voltage current etc., but characteristic impedance in those cases also we do not define, or define for with respect to some standard thing. Sometimes we define arbitrarily also. So, characteristic impedance is not so important in for T or TM type of things. Now, what characteristic impedance physical significance, as I already described, that it describes the power transport property of the structure supporting the wave. That means, how much power transfer you can make, because if you know the characteristic impedance of the line, you can choose your load impedance, source impedance properly, so that you know that whether you are able to do efficient power transfer. So, characteristic impedance is very important information when you design your whole transmission and reception structure, that how to choose your load impedance and how to choose your source impedance. So, that whatever power you are producing, you can put it to the line, and also you can extract at the line from the air. So, for that characteristic impedance is important. So, you see that it is part of a training of you, that you should understand whether to find wave impedance or characteristic impedance. Remember that whenever I have a wave, it is not guided by any structure, it is going. I want to describe some property of the wave, the definition is impedance. You know, impedance is a very important concept. We have in an earlier NPTEL lecture, we have seen lot of impedance, how to match impedance, what is the physical concept. But what is it? Actually, impedance is a whole structures information. It is a ratio of electric and magnetic field or voltage and current. So, whatever may be the electric field and magnetic field, because they are part of the excitation, so they can change. But the impedance is a property of the structure. So, a radiating structure, it has an impedance. So, it won't change. Whatever electric field you produce, it will have that thing. So, the network or the structure, its property comes out of impedance. Impedance describes that property. Your electric field, magnetic field, etc. can change, but the ratio that gives you some insight about the property. In case of transport structure, characteristic impedance give that property. In case of radiating structure, wave impedance give that property. In case of a wave, that how electric and magnetic field of the wave is related, wave impedance tells you that. In free space, it tells that whatever wave you give, but it will be some, its wave impedance will be something. So, whatever electric field you give, what will be the magnetic field, you can always calculate from this property of impedance. That is the beauty, that since impedance is there, it depends on the structure, it depends on material, it depends on frequency. So, all those things are known to us. So, whatever unknown field is there, we know that okay, if you have electric field so much, the magnetic field will have to be so much. So, power will be so much. So, I need not exactly find what. So, all this information comes to impedance. It is a very important concept in electronics. So, wave impedance, now let us calculate wave impedance of a TEM wave. So, you can see that we have found out Ex and Hy. If you put that, it becomes beta omega. Finally, you see that any TEM wave, its impedance is free of, you see this is the wave impedance. Wave impedance is always eta, no relation to which structure is making that, whether it is the plane wave that is propagating or the in coaxial cable it is propagating, the wave impedance is equal to only the material properties. Only the material properties in this case. You see, it is not a frequency dependent thing. In general, wave impedance depends on frequency, but for TEM wave, it does not depend on frequency. That is why all possible frequencies can pass, their wave impedance is same. It is same as intrinsic impedance. Now, if you have a TEM line filled with air, it will be eta naught, that is 377 ohm. If it is filled with something whose dielectric, some dielectric with dielectric constant 4, it will be 377 divided by root 4, that is 2. So, that you can find out like that. Now, also you see that this we have seen, and this is Ex by Hy, as I explained that you can also take this ratio as minus Ui by Hx, and that also is coming to be eta. Now, so we can always say that you see transverse electric component and transverse magnetic component of the field, and in case of TEM they have only the transverse component, no longitudinal component. So, they are related by this, that if you know one, you can find others, provided you need to know this. This you know from the material structure. Suppose this whole earth is now made with, suppose inside water, if you radiate a signal. So, water's dielectric constant is 80, and you can take water's permeability is roughly same as the free space. So, what will be the impedance? The wave impedance inside water, that will be this 377 ohm divided by root 80, let us say 9. So, 377 by 9, how much that will be? 9 is 42 ohm. So, I know that. So, then if I find out what is the electric field, I can tell what is the magnetic field. That is the beauty of wave impedance, etc. Now, wave impedance of TE mode, again you have expressed. So, Ex Ui we have expressed. If you put that, it becomes something. This you see that it is a function of k eta by beta. Eta was there, but you see now it is k by beta. So, k it is a frequency dependent term. So, frequency is coming here as, unlike TM mode, wave impedance of TE mode depends on frequency, because k is what? Omega square. If you remember, k was our propagation constant, that wave number. So, k is omega square mu epsilon. So, k through k this frequency is coming omega. Omega is nothing but 2 pi f whole square mu epsilon. So, frequency is coming here, materials are coming here, eta is also, eta is square root of sorry, this is k, then k eta means mu by epsilon and then beta. So, this is the, in TE mode, this is your wave impedance. Wave impedance of TM mode, again through k, that means the wave number, the frequency is entering. So, that is all. That impedance, that is why you should know when to find out wave impedance, when to talk of characteristic impedance, and how to measure impedance, how to match impedance, etc. You can see our earlier NPTEL lectures were called basic tools of microwave engineering, where we have covered impedance things, how to measure particularly, because a microwave engineer should know how to measure impedance. You see that lecture series where basic tools of microwave engineering, where that was dealt elaborately. So, you refer to that if you want to measure impedance, if you want to match impedance, etc. With this, we conclude this lecture. So, only one thing remaining, that till now we have assumed everything to be lossless, and in microwave it is up to certain frequency of it is true, but there will be loss. That means, instead of, generally we have talked of conductors and dielectrics. Now, generally an ideal conductor, it should have infinite conductivity. So, loss, that is why it is lossless. So, conductors, ideal conductors are lossless, but any practical conductors, they will have some finite conductivity, nothing is infinite. So, there will be some loss. Similarly, on dielectric, it should have 0 sigma, conductivity should be 0, it should not have through it any conduction of charge, but in real life it has some conductivity. So, there will be some dielectric loss, and that will change this whole thing, because here we are assuming in the whole thing, if sigma is changed, because J and E, they are related by Ohm's law through sigma. So, if sigma is not the ideal, then the whole structure will change. So, how to incorporate that change, or how to find out what is the loss that takes place in microwave transmission, that we will see in the next lecture. Thank you.